webinar, we will be talking about modeling and simulation with MapleSim and Maple. We will be focusing on a specific example, and that is a tracked vehicle. So let's have a look at the items that I have for this webinar. We'll talk briefly about the modeling approach for the tracked vehicle, the track geometry. We will be using Maple to generate the data points on the track geometry. We will use MapleSim to visualize that track, having items go around the track geometry to visualize the motion. We'll look at the terrain generation, and we will be using Maple for that. And also combination of Maple and MapleSim through the use of custom components to model the contact between the track and the uneven terrain. Look at briefly at steering for a track vehicle, and the steering also is done by the help of Maple. And we'll briefly look at using or creating user libraries based on a completed vehicle for reusability, and a summary. So the hope of this presentation today is to give you a sense of modeling and simulation with both MapleSim and Maple for this particular example in the realm of multibody. Okay, so the modeling approach. For this simplified track model, the actual dynamics of the track is not modeled. We use only visualization to bring track to life. For the contact between the tracked vehicle and the uneven terrain, we will be using a sphere to plane contact. And this sphere to plane contact, basically we will have local tangent to the terrain. We will create planes for that, and then include the equations for the contact with friction between a sphere and a plane, and include that. So to just have a visualization of what we aim to do, we'll have spheres located at appropriate locations that will emulate the contact between various wheels with the ground, and then add visualization on top of that so that we can have a realistic looking simulation of the track vehicle. Okay, let's start with the track geometry. Here a very simple geometry is chosen. We'll have 5 parameters to design or define the geometry. The distance between the 2 big wheels, the radius of the big wheel and the small wheels, and the offset, the vertical offset between the center point of the big wheels and the small wheels, and also the distance between the leftmost and rightmost small wheel. So we'll get 5 parameters, and we will have a relationship for the angle of the tangent line connecting the 2 circles. Using Maple, we can write vectors that lists points of interest for every segment of the track. We'll keep these relationships that discretize the curve parts of the track, and we'll also define the straight parts of the track. So this will give us the geometric definition of the track. What we will do with this definition is we will create numerical data based on a given set of those 5 parameters, and we will save them using the Excel tools package of Maple to a file. We will then use this file within our MapleSim model to have a reference for motion of the segments along the track path. Here is a sample of the data saved. It will have 3 columns, the first being the cumulative sum of segments lengths, starts from 0 and goes to the total length of the track. And for each point, we will have, or each segment, end of each segment, we will have an x and y coordinate that were calculated by the equations that I showed in the previous slide. So here we have the geometry defined, and we now pass that to MapleSim from Maple. We do that by using a feature in MapleSim where you can attach a data file to your MapleSim model and then access them through a component called lookup table. So we'll look at a subsystem for the track visualization. The subsystem, as it is created, will have two inputs or two ports. One is for the speed signal, so the driver or the controller will provide the speed for each track, left and right, and that is used inside the subsystem. And there's also a multibody connection point to hook the track to the rest of the moving vehicle body. So in this case, looking inside, we have subsystems that each one of them inside each subsystem, here we have 20, have the information for the Excel data that we just saved, and we'll move a visualization cylinder across that track with the appropriate offset. So looking at each one of those subsystems, identical subsystems, we will see that we have the lookup table component, two of them, and a motion driver. So in this case, because the vehicle will be aligned with x-axis and the z-axis is up, pointing upwards, we'll use the data that we have calculated to move y and z coordinates, and this is the visualization at the end. So looking at the track, it basically will accomplish having these cylinders move along the geometry defined by the 5 parameters that we mentioned before. So now we need to have this combined with the rest of dynamics of the system. So this part is not dynamics, this part is for visualization. And what comes next is the rest of the dynamics of the tracked vehicle and how it interacts with the uneven terrain. But before going there, we can enhance our visualization by adding toothed wheels to our visualization of the tracked vehicle. Here I'm showing a little Maple application that was created using Maple programming language and the embedded components that are provided, that are available within the Maple environment. So we have control over the inner and outer radius of the sprocket looking wheel and the number of teeth and some angles and definitions. So we can play with them, select the one that is appropriate for our current application, and use Maple packages to export the 3D representation of this profile as an STL file. Just like we did with the Excel data for the track geometry, we will attach this STL file to our MapleSim model so that we can access it through the CAD component from the visualization subpalette of the Multibody library. So what we see here is the command in Maple that saves this graphic as an STL file. Bringing those data to our MapleSim model will enhance the visualization that we will see shortly. But now that we have chosen the number of teeth in each big wheel and small wheel, we're basically putting some constraints on the segment length of the track segments and also the distances between the big wheels. So now the geometry of the track and the segment length of each part of the track now gets tied together through the radius of the wheel, a big wheel and a small wheel, and also the segment length. So to do that, to be able to make a calculation so that the visualization looks good, we need to do a bit more calculation. Here on the right hand side, you see the same lines that define the different segments of the track geometry. The same equations are rewritten here, but what is different here is that they are put inside a procedure. So this is Maple programming language. We have created a procedure here that gets the 5 parameters that define the geometry of the track and calculates the total length and outputs that at the end. What we can do with this procedure is that we can use that to do some numerical work. Here, what I intend to do is, given some of the parameters, like the d, the distance between the leftmost small wheel and the rightmost small wheel, the small wheel radius, the big wheel radius, and the offset, what would be the distance, the appropriate distance between the two big wheels if I want to have the total length of the track to be 12 meters. I can just use a command like this. So I'm putting the function here, this procedure inside and create an equation from it. Length with all these parameters equals 12, and solve numerically for L, which it does instantaneously almost, and give me the value. I can quickly check that value to see how good is the results, and I'm satisfied with that. So I can use this length inside my MapleSim model, making sure that the selected segment lengths, number of segments, and the wheel radius, and also the number of teeth on the sprocket, all of them are now match. And that makes for a good visualization, and the pieces won't go out of sync. I have included this little work here just to give you a sense of some of the Maple work that users can do to enhance their models as they creating multibody or any type of model within MapleSim environment. Maple symbolic numeric environment is quite handy in enhancing that modeling experience. Putting them all together, we get something like this. We already saw the cylinders going around the track, and now we see the big wheel and small wheel visualization that with the appropriate calculation of the number of teeth and the geometry, they all look synced and make for a good visualization of the track vehicle. So far, what we have done has basically no dynamics in it. What we have done is Maple work for geometry calculation and MapleSim work for visualizing it or bring it to life, but no dynamics. Another view of the track in action in 3D. We will talk about the steering, basically controlling the left hand and right hand side separately a little later on in this presentation. Okay. Let's talk about ground contact. So as I said, we're going to use sphere to plane or ball to plane contact, and for that we have another subsystem similar to the subsystem you saw previously. We use MapleSim grouping capabilities to make models more tractable and easy to understand. So this one is the ground contact subsystem. It also have 2 ports. One is again the speed signal. The same speed signal that goes to track visualization comes here because we want these spheres to turn with the appropriate velocity. So when we do the calculation of the relative velocity between the contact patch and the stationary ground, we get the right values, and also be able to calculate the friction forces or control the friction forces, thus controlling the motion of the track vehicle. And also we have a multi-body connection port port to connect this force subsystem to the rest of the system. So we have, as I mentioned, spheres that are located at appropriate point, and we make a match with this rigid body frame, which is a coordinate transformation, to coincide with the places where we have the visualization for the big wheel and visualization for small wheel. Each of these visualization points, you can see that they're connected to this identical subsystem, and these subsystems are the ones that providing the relative force between the local, whatever this wheel will see, local terrain, and the contact force. Okay, let's look into the contact force a little bit more detail. As I mentioned, the local ground elevation information is used to estimate ground normal. We will talk about the terrain generation a little bit later on in this webinar, but for now we assume that we have the numerical information that represent the terrain. Basically, for each x and y, we have a z value that we can use inside the lookup table and interpolate to get a smooth uneven terrain information. For the calculation of the forces, normal forces, we use a linear spring damper, and we use based on the projection of speed, or the relative speed of the contact point and the ground, we calculate the friction force. This is done inside that subsystem, the yellow subsystem we saw in the previous slide. That includes all the calculation of the forces. These sensors provide the position and velocity of the center point of the sphere, and also the angular velocity as it rotates, given the speed signal by the vehicle driver. They calculate both the forces and the torques that are applied here. Well, actually, there are forces here applied, but because we are applying the forces to the center, we also need to calculate or account for the resulting moments as well. So that's why we have both forces and moments. So this calculation is done inside a Modelica custom component. And I'm just going to give you a quick review of that Modelica custom component. We use Maple to bring custom components written in Modelica to MapleSim as a custom component. Later on, we will see another type of custom component that is not based on Modelica language and gives ability for the users who are not familiar with Modelica to just use naturally written mathematical equations to create custom components as well. So here, let's just break this down. First part, we have to define some parameters for our component. Just like any MapleSim component that you drag to canvas and start connecting, most of the components have parameters that the user can adjust. And this is one way to define parameters that user can manipulate for a custom component. So this is the parameter keyword definition. We have a characteristic distance to define the tangent to the uneven terrain. So that's the epsilon, the ball or sphere radius that we are using to calculate the distance from the center of the sphere to the local tangent is also a parameter. The stiffnesses and damping coefficients that I talked about are here. And we have a coefficient of friction and also a smoothing factor because we will use a tan H definition to implement the friction. And we have some other parameters for what data set to use. As I mentioned before, in MapleSim you can attach your data files, and this type of definition will allow you to get access to that attached data set inside a custom component. And we also can can define what type of interpolation we want to do for that interpolation, whether it's linear segments or smooth interpolation. Okay, the second part is some variables that we need to define. Actually, these are the inputs and outputs to our custom components. Of course, they are also variables. So we have the position velocity and angular velocity. If you remember, from the picture of the subsystem, we had two sensors that provided these information. So this is where the signals get connected graphically. And also in the subsystem, we saw that this custom component is set to calculate forces and moments. So this is where the outputs are connected to those applied force component once we have created the custom component and we get the graphical icon. So these are the internal variables that are needed to define various calculations. We will see them in action pretty soon. So this is the equations of the system. So as you can see, I have vector type calculations. So I define the 3 points on the 3 vertices for a triangle. The x and y is set with the parameter epsilon that designates how big that triangle is. The z value for each vertex is done by interpolating the terrain information. We'll talk about the terrain information as well. Basically, I'll pass x and y, get z for the first point, pass x and y, and get z for the second point, and so on. We do a cross product of the two sides of a triangle to find the normal to the surface or the local tangent plane to the uneven terrain. We normalize that vector to get the unit vector, and also average out the 3 points to get the resultant point for the contact. We calculate the distance between the center point and this local tangent plane, and calculate the spring rate and damping, and also put another line here so that only apply normal forces when the sphere and the plane touch each other. When they are away, set the force to 0. We do V plus omega cross R for calculating the relative velocity of the contact patch and the ground, and use that velocity and the direction of that velocity vector for calculating the friction force vector. Another cross multiplication here, a cross product to calculate the resultant moments of this friction force with respect to the center point of the sphere or wheel. And the total force of normal and friction will give us the total force applied here instead of here. So these two are summed and put here, and the torque is also accounted for. So this makes the custom component for contact between the sphere and the uneven terrain. For the uneven terrain, of course, you can have data coming from another source. Maybe it's a measurement of a surface. But here we use Maple again to generate that data. So here I have a nonlinear function of x and y to basically create a ridge that I'm hoping the track vehicle will be able to negotiate. Some parameters using Maple plots package to display it, and also use this similar Excel tool package as we saw before to save that data to the MapleSim model. Putting them together, we'll see the visualization come to life with the interaction of the spherical contacts with the uneven terrain. Let's have a look at that quick animation again. And it is you can see that also the terrain generated is also added as an STL file to MapleSim to make it all very harmoniously work together. Now now that we can have our track vehicle go on a straight line, let's look at the steering. This is just an example. This is not meant to be the actual steering. This is just something to make our current simple track vehicle steer. Here we use another way, as I mentioned, for adding customized components to a MapleSim model. We go to Maple and use appropriate template called the custom component template, and I'm defining two piecewise for the velocity of left hand side and right hand side tracks, as you can see by typing the equations here. Let's have a look at what these two piecewise functions do. So based on the steering signal, so this goes from -1 to 1, I'll change the commanded velocity from the negative of the maximum velocity for one side to the positive of the velocity for the other side. And by changing the steering signal from -1 to 1, I can reverse the velocities, having both tracks have the same or complete opposite, and all the points in between. Of course, there can be many other types of control for the two tracks. You can have them completely individually controlled, but here I have a speed signal and also a steering signal for controlling the track vehicle. And if I put them all together, you can see an example here as the spheres interact with the ground due to the friction and different commanded velocity of rotation. They produce torque for the whole body and causes the track vehicle to steer left and right. Now, we saw a couple of subsystems that were created in the process of modeling the track vehicle in MapleSim, and I just want to take a minute here to talk about organization of a model. So this is the top level, the look of MapleSim canvas as the components are put together for this model. We have the track vehicle here. Inside it there are multiple subsystems, some of which we saw. We have the CAD visualization here for the terrain got generated and attached to the MapleSim model. We have a couple of parameter blocks that include the parameters for the geometry of the vehicle, and also some control over whether we want to include the ground or not. Signals coming in, the speed signal and steering signal for having that visualization that we just saw. And these are just sample ones, the user can easily change them. So we can have all the subsystems that we have created and put them inside a hierarchy inside MapleSim. Instead of having them all in definition sections, we now in MapleSim can generate these hierarchies that looks like they look like any other palette in MapleSim, and the users can, once they have created this hierarchy, organize their subsystems into groups that make sense. They can make them a user library and attach them, or basically bring them up to the main level of MapleSim graphic user interface, and even share them with others so that they can use the same pieces to create the same model or other more complicated models, or enhance their own models that they have created. This subsystem or this track vehicle model in MapleSim also includes some attachment. We refer to all of these as we were going through this presentation. There was a Maple worksheet, as you can see, that we used to generate the visualization for the sprockets or the big and small wheels. We had another Maple worksheet to generate the terrain. We had a worksheet that we used to do a numerical solve on the track length procedure to find out the distances. and also another worksheet where we design the geometry of the track. We have a couple of custom components. The differentiator is the one that I have showed for the steering, basically set signals to left and right side. This is an equation-based custom component. And we talked about the ground contact. This one was a Modelica custom component, and these basically sit under custom components section of your attachments. We had data files. We have the terrain data that was created by this Maple worksheet and then attached. We had the track geometry data points that we generated and attached, so that goes under data sets. And we have used the Sprocket tools to create two for small and big wheels STL files, and also one for terrain. So the terrain, so they all go under CAD images. So this is how we use the predefined sections in the attachment palette of our project. These are all the enhancements that you add to MapleSim to improve your models and visualize them better. So the hope was that this presentation, being a relevant system that people would want to model in MapleSim, but the other aspects of this presentation was to give you a sense of how we can merge the MapleSim modeling environment where we create dynamic multi-domain system level models with the power of Maple to both enhance or expand our modeling and also help with the visualization or creation of parts that we will use in our model. We saw use of symbolic and numeric computation in Maple. We saw the example of using programming in Maple, and also working between MapleSim and Maple when we generate files, attach them to the MapleSim model as well.